We are living in a plastic age, but the real threat isn't just the bottles or the bags we can see. It's what they become, an invisible invasion of microplastics. Those tiny particles, which are smaller than 5 millimeters, are now literally everywhere. The core problem is the design of conventional plastics. Their strong polymer structures resist degradation, allowing them to persist for centuries. Then the microplastic particles goes into human body by the fish we eat in, causing potential dangers to our immune system, genital system, and cardiovascular system. So the social challenge is clear. We must break this cycle. We cannot rely solely on imperfect recycling or reduction efforts. We need a fundamental shift. How? Some chemical engineers are pioneering in the use of large-scale fermentation in bioreactors. We can convert renewable biomass like corn sugar or cellulose into monomer building blocks. They are then polymerized into bioplastics, such as polylactic acid or PLA. However, the challenge is equally significant. It requires completely overhaul of our manufacturing infrastructure and faces hurdles in cost, performance, and potential competition with food resources. To discuss the problem further, we invited our national scientist, chemical factory manager, and CEO for chemical company to help us illustrate an alternative future solution and its pro-con analysis.
A magnetic continent shell bichar is suitable for absorbing antibiotic. The reduced magnetic particle cluster after absorption indicates strong binding with pollutants, and this is the SEM image of bichar after tetracline absorptions. Rice strong base magnetic bichar's extensive covers of macamite on the surface enhance absorption capacity for heavy material, dyes, etc. We finally choose magnetic bichar as our promising solution. The absorption rates of 98.7% and the ability to be reused over 20 times are very impressive, far exceeding traditional activate carbons about 30%, which makes it highly persuasive both technically and economically. Magnetic bichar is suitable for centralized and large-scale treatment scenarios, such as the advanced treatment at the end of the urban sewage treatment plant, effectively preventing microplastic from being discharged into natural water body. Natural polymers are applicable to undead centrals and small-scale scenarios, such as rural areas and household water purified, offering a safe and cost-effective solutions. High cost effectiveness. The raw materials are cheap and readily available, and the recycling process is simple, indicating that the total cost is relatively controllable when applied on a large scale.
This innovative material offers three key advantages for microplastic cleanup. It transforms agricultural waste into a useful water treatment tool, embodies circular economy principles. Its magnetic properties enable complete recovery from water, solving a major operational challenge. The proper structure effectively traps microplastic particles while being environment friendly. However, significant challenges remain. Real-world performance drops dramatically as natural organic matter competes from absorption sites. The material cannot capture hazardous nanoplastic due to the size limitation. There is also risk of secondary pollution when captures microplastic detached due to environment change. Most critically, saturated biocarbon become new plastic waste with no viable regeneration or deposit method. While promising, this limitation currently prevents particle large-scale application, highlighting the need for both technical, advanced, and source-reducing strategies.
Now I'm going to talk about the challenge and the future solution for MRBs. MRB accepts excellent microplastic absorption due to its high surface area and magnetic properties. However, real wastewater and surface water contain natural organic matter, oil, and colloidal particles that compete with microplastic for absorption site. This competition can drastically reduce MRB efficiency by blocking pores or forming surface coating, leading to underestimated performance in field conditions. Surface structure optimization through control activation process increase porosity and functional group density, improving microplastic affinity. With the increase of amount of activated compound added, we gradually increase and finally tend to balance. The surface of the RB and within the pore channel increase the roughness due to the attachment of iron oxide. The MRB after the absorption of microplastic is shown in the picture, you can see that, where many more homogeneous round particles are evident on the surface, indicating that the microplastic were absorbed onto the magnetic material. Also, the surface engineering modifications are essential. Activation of biochar with diolate acid, alkalis, and oxidant can create additional pore and functional groups, for example, carboxy or hydroxy groups, enhancing physical absorption and chemical bonding with diverse microplastic type. For instance, acid treatment improves cation exchange capacity with alkaline activation increased surface roughness, favoring microplastic attachment. Also, thermal recovery at 500 degrees not only regenerate MRB but also align with circular economy principles, reducing waste and costs. The number of circles was increased. The saturated magnetic intensity of MRB decreased slightly, indicating that phases affect the magnetic properties of the material. The electrostatic attraction between the MRB and microplastic was also weakened. So the absorption of performance of the MRB decreased after several circles. However, after 5 circles, the absorption of microplastic onto MRB remained higher than 90%.